Hi, welcome back to AP Physics C, Electricity and Magnetism. You're almost done. You got 3 videos left. You got RL circuits, LC circuits, and then finally Maxwell's equations. The great thing about Maxwell's equations is they're just a set of equations that we talk about. We don't do a lot of calculations because we've already done them throughout this course. So in this video, we're going to look at the RL circuit. So an RL circuit, right, is any circuit consisting of a resistor, an inductor, such as a solenoid. In the last video, that was our example problem. We talked about a solenoid, and an EMF that are in series or parallel, okay? And so those are RL circuits. So this is our symbol for a resistor. This kind of coil-looking symbol, that's our inductor. Some of these equations will look like when we talked about RC circuits. So we're going to have a look at charging versus discharging with like the switch closed versus opened. And so let's keep talking about this. So what we need to do is to solve RL circuit problems, you're going to solve Kirchhoff's voltage rule to find the necessary equations. So remember, Kirchhoff's voltage rule, right, tells us that the total voltage minus the voltage across those two components will equal 0. Now, that may show up in a free response question to derive the expression for, let's say, the voltage across, or determine the current, right, where both the L and the R components have currents in them, okay? And they may say discharging versus charging. So an inductor with self-inductance L is used in a single loop circuit to stop the current from reaching its maximum value instantaneously. So the second you flip that switch, due to the inductor, right, the current that is going to flow through the resistor will not be a maximum. In fact, it's going to be 0 the second you flip the switch, okay? And we will run into our time constant again. So the time constant for an RL circuit or resistor inductor circuit is simply tau equals L over R, okay? And basically it just tells us like how much time is really changing the circuit, the voltage, and so forth. All right, but here's a little bit of help, right? So if you take that Kirchhoff's rule and when you close the switch, you are charging the system, and when you open the switch, you are discharging the system. Okay, and so what we want to do is if we want to find the current, right, we're going to do our max current times 1 minus e to the negative t over tau. Okay, and so what happens is the resistor, right, will have a max voltage times 1 minus e to the negative t over tau. Again, all this stuff is derived through this equation here, right, the Kirchhoff's voltage rule. And the inductor will have, and all these are Vmax, right, a value of e to the negative t tau. Now, when you open the switch, now it starts to discharge through the inductor. Current starts to flow more. And so the current will be Imax times e to the negative t over tau. And then your voltage across the resistor will be e to the negative t over tau. And then your inductor will be e to the negative t over tau. So what you actually kind of see is these two end up, once that switch is once it's discharging, it tends to be the same. Okay, so let's look at an example problem, and we're going to refer back to some of those equations to help us. So we have a solenoid with an inductance of 25 millihenries and a resistor with a resistance of 8 ohms are connected to the terminals of a 6-volt battery in series. There's also a switch in the circuit, okay, that tells us charging versus discharging. So A, immediately after the switch is closed, find the potential drop across the resistor. Well, remember what we said when we talked about the notes? The first thing is this voltage drop will be 0, right? And why is it 0? It's mostly because the inductor is what's really going to kind of collect up that charge. And if you actually use the equation, right, because we're charging it, so we would do the 1 minus e to the negative t over tau, right? What happens is this term here, because t would be 0, that becomes 0, or excuse me, that doesn't become 0. That becomes 1. Right? And you end up with 1 minus 1. Well, 1 minus 1 is 0. So that tells us, like, the second you close that switch, your voltage drop across the resistor is going to be 0. Okay? Now, part B says, okay, what is the final current of the circuit? Well, that's very easy because essentially the inductor, right, is removed from the circuit. So then it's just the resistor. And so we just do I equals V over R. We go back to Ohm's law, right, which we learned in Unit 3. Okay, and so we just do 6 volts over 8 ohms, and that tells us that the final current would be 0.75 amps. So what this turns into, you know, Imax, not the movie theater, but the maximum current, right? The final current. So part C says, what is the time constant? So C is looking for tau. Tau is L divided by R. Just like when we did resistor capacitor circuits, tau is RC. So like we're doing some sort of manipulation, and we're going to do tau equals L over R. That shows up through the derivation of these equations. I'm not going to, you may have to solve for it at some point in time, but I'll give it to you here in these videos. Not to the -5th. So it tells us we have 25 times 10 to the -3 henries. Divided by our resistance, so 8 ohms. And so our time constant is 3.125 times 10 to the -3 inverse seconds. Okay. And so what that is, that would be seconds. I apologize. That is S. So that's telling us, like, all this stuff that happens, the changing of the current, the changing of the voltage happens, happens every 3 milliseconds, basically, is what that's saying. Okay. All right. Part D says find the current after one time constant has elapsed. So what that is saying, that our T over tau is equal to 1, right? Because we're going to do 3.125 times 10 to the -3 seconds, and we're going to divide that by our time constant, which is 3.125 times 10 to the -3, right? So it's telling me that the exponent is just going to be equal to 1, right? And so we use our Imax or I equation. So I equals Imax times 1 minus e to the -t over tau. Okay, but we said that -t over tau is 1. So Imax times 1 minus e to the -1. Well, that e to 1 minus e to the -1 ends up being, I didn't write it down on my paper, but e to the -1 ends up being 0.367. And our Imaxes are 0.75. So we get 1 minus 0.368, really. Okay. So 1 minus 0.368 is 0.632. And we multiply that by 0.75, and we get 0.74 amps. I forgot the second 4. Okay. So that's telling us that after one time constant, the current that is in our circuit is 0.74 amps. So we're building up. And you may do it as like 2 time constants, 10 seconds, right? Where are we at? Okay. So you would just plug in whatever. So if it was, a time constant of 2, right? Well, instead of plugging in -1, you're going to plug in -2, okay? Which then changes this number here, which then will change the amount of current. Okay, so 2 videos left. You got LC circuits, and then you have Maxwell's equations. And we'll see you on that side.